Welcome. This is Jim Pytel from Columbia Gorge Community College's Renewable Energy Technology Department. This is EET 121, Digital 1, and today we're going to discuss arithmetic operations with signed numbers. Specifically, we're going to discuss the adder. Okay, as we discussed in some of our earlier lectures, pretty much all multiplication, division, subtraction, and addition is done with an adder. And some of you guys have been looking at me like I've been smoking crack when I talk about that. But it's true. Pretty much everything, all these arithmetic operations can be done with an adder. And how do you do this is with 2's complement. So I'm going to go over a couple of these things. And specifically, I'm going to start with addition and go over 4 cases. Basically, where the numbers to be added are both positive. Second case where there's a big positive, a little negative. Third case, little negative, little positive, big negative, both negative. This covers pretty much all 4 cases here. What's going to happen is you would expect when they're both positive and they're added together, that's going to be a positive result. If there's a big positive number added to, a big positive number and a little negative number is added to it, you would also expect a positive result. If there's a little positive number and a big negative is added to it, it's a negative. And if they're both negative added together, one would expect it to be negative. So when they're both positive, let's talk about just 9 plus 6. So 9 represented in binary is 1001, 60110. Okay, so add them up just like we've done. So it's 1 1 1 1. Go ahead and put that into decimal notation. That's 15. Okay, pretty simple. It's true form. It's represented in true form. Okay, so big positive, small negative. Okay, let's take our 9 out of a negative 6. So 9 in 8-bit notation is that. Now we need to represent 6 as our 2's complement version of it. So that's 1, 2, 3, 4 ones, 5 ones, 0, 1, 0. Now add those up. 1, 1, 0, 1. We have to carry this 1 bit right here, right? So that's a 1 up there. And now 1 and a 1, that's 0. And we have to carry. And you're going to be performing these successive carries all the way through. So it's all zeros, and you get a final carry bit of 1. Toss it. This is the true representation. So it's 1, 0, 1, 1. What is that? That is 3. No, it's not. What did I just do? Oh, geez. Right there. Because 1 and a 1 is 1, 0. It's not 1, 1. Sorry, guys. Does everyone see that? Okay, so it is 3. It is the true representation. You've just taken this final carry bit and discarded it. Okay, case 3. We got a small positive number and a big negative number. Let's do, where is it? 6 minus 9. And again, representation of 6 is that. Let's make it 8 bits. Representation of 9 in 2's complement is that. You're going to add them up again. So basically all you do, and I'm not going to make a mistake this time, 1. 1 and a 1 is 0, 1 with a carry bit there. Now we got a 1 there with another carry bit, 1. Okay? And then it's 1, 1, 1, 1. Okay? So what is this? This representation is 2's complement. So what is this? It turns into 0, 0, 0, 0, 0, 0, 1, 0. And then we got to add our 1, 1. That's 3. That's the 2's complement. Excuse me. This is -3. It's the 2's complement version of 3. Okay, so we've just performed a, again, it's a 6 plus minus 9. It's the same as 6 minus 9. Using 2's complement version of -9, we came up with the correct answer of -3. Okay, so both are negative. Let's do, I'm sticking with the same number so we're not going over. Okay, the 2's complement representation of 6 is again 1, 2, 3, 4, 5 ones, 0, 1, 0. The 2's complement representation of 9 is 1, 2, 3, 4 ones, 0, 1, 1, 1. Again, you're going to add them up. So it's 1, 0, 1 with a carry there, 0, 1, 0, 1, 1, 1, 1, 1. We're going to have a final carry bit. Discard it. What is this representation in 2's complement form there? That is going to be, convert this thing as 1, 2, 3, 4, 0. And remember, we're going to convert it. We're going to add our 1 to it. This is 15. So that means the 2's complement representing is -15. You can also do, remember, there's another method of doing this. 2 to the 0, 2 to the 1, all the way through, but then this thing at the end is -2 to the 7th. Same thing over here. This is -2 to the 7th. That's +2 to the 6th, 2 to the 0. Add them up using the sum of weights. Okay, so what we've shown here is kind of this using addition. We've done both addition and subtraction. So you're using the 2's complement. Anytime it's a negative number or you want to subtract a number, you just use the 2's complement of the number. And it comes out. And again, if it's one of those answers where it's negative, it's going to come out the 2's complement. What you can take away from this thing is use the 2's complement, add and discard the final carry bit. Okay, there's this thing called overflow that we need to discuss though. It's a situation when numbers are added together exceed the number of bits allocated and the discard number becomes important. See how this thing right there is shifted over? Let's say you're adding, I don't know, like 1 million plus a million, and you've only got a certain amount of bits, and it's not going to take 2 million. Basically you're adding those together, and those bits are carrying over into a region that you don't have space for. So when there's an overflow error, again, it's exceeded the number of bits allocated, and the discard becomes important. So that's when you might have to go to a double precision